Okay, so in this movie clip, let's delve into some great details on how the PMP BJT is working qualitatively, not quantitatively. So in the last movie clip, we have mentioned that the forward bias, the emitter PN junction, that was a kind of magic box that I have explained, right? So forward bias, the emitter PN junction, which would become an resource for supplying tons of minority carriers into the other PN junction, right? So this emitter forward bias emitter PN junction. Let me draw the cross sectional view. P and P. So in this reverse biased PN diode, right? We would like to increase the saturation current, right? For that purpose, we can place a new magic box to supply the holes or supply the minority carriers into this N site, right? For that purpose, we would like to place a P plus region because it has a tons of holes, right? Because it is heavily doped. So this P plus and N, another PN diode, but to supply many holes into this N side, that should be forward biased, right? So a forward biased PN junction, but named as that, is going to supply tons of holes. So it is going to emit out many holes into this N side region, right? So that this P side can be named as the emitter. So this forward biased emitter PN junction, this guy, is used what? To inject what? Minority carriers. Why minority carriers? Yeah, here once hole has been delivered to this N side, the hole becomes minority carrier. So we would like to inject many minority carriers into this N side. Okay, and this magic box, which was forward biased emitter PN junction, is used to inject minority carriers into where? Yeah, the vicinity of reverse biased collector PN junction. So collector PN junction means this part, the original PN diode, right? So, but that is reverse biased, and now the saturation current is flowing. So reverse biased, this second PN junction. So near to this PN junction, second junction, we would like to inject many minority carriers into it. Okay, so please have your own time to deeply understand the very first sentence in this lecture note. If not, you're not eligible to move forward. Okay, please go back to your textbook and have your own time. How come the forward biased emitter PN junction would become a magic box in terms of supplying many minority carriers into the second or original PN diode, which is under reverse bias, and we would like to improve and enhance and increase the saturation current of the reverse biased PN diode. For that purpose, we can place a forward biased emitter PN junction, then we can supply humongous number of minority carriers into the reverse biased PN junction. So please have your own time. Otherwise, you're not ready to move forward. This is very important sentence and important thing that you should understand. Why is that? Because I have put two different PN junctions, one of which is forward biased, the other of which is reverse biased. So forward biased PN diode plus reverse biased PN diode. What would be the result of them? Yes, bipolar junction transistor. Why is that? Yeah, we're gonna study it today more. So again, a forward biased emitter PN junction is used to inject minority carriers into the vicinity of a reverse biased collector PN junction. Then the thing that we can expect is this. The collector current. Collector current means how many current can flow out of the collector electrode, collector region. Okay, this collector current can be controlled and governed by what? Base emitter junction. So take a look at the cross-sectional view of this PNP BJT. So In this PNP BJT, I would like to increase the saturation current. I not in this reverse biased PN diode. For that purpose, I have put heavily doped P plus semiconductor right onto the N side. So in the end, we are gonna build up one more P plus N junction, which is forward bias because we would like to supply many holes into the N side. Okay, but now I would like to control the total amount of current in this P part, named as I sub C. But this I sub C is nothing to do with how much voltage has been applied in between this emitter to collector. I mean, the VCE is nothing to do with, no, IC is nothing to do with V sub CE. So the voltage difference between collector and emitter is nothing to do with collector current. If I draw the circuit symbol again for PNP, emitter, collector, base, and IC, right? This IC, the total amount of current coming from the collector, is nothing to do with emitter voltage. I have to say emitter voltage instead of EC. Yeah. Okay. So VEC, emitter to collector voltage difference, is nothing to do with I sub C. Well, at a first glance, that sounds weird. Why is that? Because this is, kind of register. So three registers so that, hey, the voltage difference between emitter and collector would may control the total amount of current flow. How come this current flow is nothing to do with the VEC? That sounds weird, but that is real one. Why is that? Because this is transistor. So going back to the definition, original definition of a transistor, transistor has three terminals. One, two, three. One, two, three. And the current flow between two terminals, say terminal 1 and terminal 2, is nothing to do with the voltage difference between those two terminals. But this current flow I12 is fully dependent of the third terminal, say V3. Okay, usually the terminal 2 can be used as a common node so that 3, 2 voltage difference between terminal 3 and terminal 2 would govern the current flow between node number 1 and node number 2. So number 2 is common for voltage and current. Anyhow, this I12 is nothing to do with V12, but is something to do with V32. This is the basic idea of transistor. Now, with that in mind, let's move on to this part again. I sub C, collector current, is fully controlled by VBE instead of VEC. So VEC cannot control the total amount of current flow in collector region, but VBE, base emitter, voltage difference, this part, right? This part, P plus N junction, how much voltage has been applied between this P plus N junction can control and can result in the total amount of current flow in collector region. At a first glance, again, it sounds weird, but this is the real transistor and this is the ideal transistor that we would like to pursue and we would like to design in IC chip. Okay, so with that in mind, now it's time how to implement this real and ideal transistor function. Again, this NP junction is reverse biased one. So here VCB right? C is p-type, base is n-type. So this voltage difference between two p-n region is negative, which means this p-n diode is reverse biased. Okay, and the saturation current flow from N to P should be enhanced. How? By increasing the electrical, by increasing what? Yeah, as we have learned, electrical injection of minority carriers into the vicinity of the junction. So again here, the minority carrier as a whole has been supplied from the P plus region, which has tons of holes because this is a P plus region. But to supply holes into the N side, this PN diode should be forward biased. Okay, so that's the reason why emitter to base P to N, the voltage difference should be positive. So VEB, emitter is P plus, base is N. So this PN diode, voltage across this PN diode should be positive, forward biased. Okay, then, then this current, the final current flow detected in collector region has been fully controlled by this forward bias voltage. Why is that? How much hole has been injected into the N side region, that hole will be delivered to the P side collector. So how much energy barrier height has been lowered by applying base emitter to base voltage? We can fully control the collector current. This is the key idea. How come two PN junctions, P and P in the end, can work as a transistor? Okay, so first the PN, P plus and emitter base should be forward biased, and the second PN junction, base collector junction, should be reverse biased. Then the collector current can be 100% controlled by the third terminal's voltage, in this case, emitter voltage. And herein the base would be common. Okay, then we can call it, this transistor works in active mode. Okay, if you're very familiar with the MOSFET is works in linear mode or in saturation mode. So this active mode can be matched to the saturation mode of MOSFET. Okay, so if you're not familiar with the MOSFET, don't worry too much. I'm going to explain MOSFET more in detail in the near future. Anyhow, here, memorize the word active mode. The meaning of active mode is emitter base PN junction is forward biased and base collector junction is reverse biased. Then we can expect the collector current is not controlled by collector base voltage, but controlled by emitter base voltage. Okay, again, simply speaking, the terminal 1 to terminal 2 current flow is nothing to do with the voltage difference between terminal 1 and 2, but something to do with the voltage difference between terminal 3 and terminal 1. That's a key idea of transistor. So I guess I have a few times I have repeated the basic stuff for transistor. If you don't have too much knowledge on transistor, please repeat this movie clip again and have your own knowledge and idea what the transistor is. Then this PMP is a one way to implement the idea and conceptual transistor. Okay, all right. So now let's slightly switch the gear and take a look at some more current component in each region. Okay, so here I have done numbering work. Number 1, number 2, number 3, number 4, number 5 things. So basically this is a P plus and P BJT. So emitter current, base current, and collector current. If I draw the circuit symbol for this PNP, emitter, collector, base. So we are not following the IEEE signing convention. So as BRS done, IE is equal to IB plus IC. Okay. All right. So now this IE whole current, right? Because this is a P plus reason, and this a PN diode is forward bias, so many holes can be injected into the N side. And the thing that we would like to expect and we would like to hope is this: all the holes can be well delivered, 100% delivered to the collector. That's what I want to have. But in rear, this is anti-Brisson. So as we have learned in p-n junction theory, the holes injected into the N side can diffuse into this N side quasi-neutral region. However, there is a electron hole recombination to be happened in this N region. Why is that? Because hole is a minority carrier, electron is majority carrier in this N region. So part of the hole injection, would be used for electron hole recombination. But this recombination would become one of the component for consisting of this base current. Okay, so some holes now in number one, some holes injected into quasi-neutral base region would recombine with what? With electrons in N-type region or in base, right? In this case. So I'm talking about this part, right? Some holes means, yeah, you think about this amplitude of this arrow, I mean the height of this arrow, and part of it, I mean this slight part of it has been used to recombine with electrons. Okay, and take a look at the second one, number two. What is number two? Number two is, most holes injected into the base diffuse out, right? I'm talking about this. Most of holes are injected into the base, and most of means this guy, right? Part of it this, but most of holes can diffuse toward what? Where? Toward collector junction. Collector junction means this part, okay? The depletion layer in this second PN diode. Okay, collector junction, depletion region. So these holes are now swept across into the collector. So I mean, most of holes coming from the P plus region, right? Let me change the color. Yeah, all the holes are here, and most holes are here. So most holes injected into this base region, right, can diffuse toward the collector junction, and they are swept because there is a electric field, built-in electric field in this depletion layer, so are swept across the depletion layer, and in the end into the collector here. Okay, that is number two. Okay, so this arrow indicates number two and number two. What the number two is, the most holes injected into the base can diffuse toward the collector junction depletion layer, and they are swept across into the collector. Okay, so this current component IC, or number two, is defined as collector current. Okay, so whenever I'm saying collector current, you should think about these most holes injected into the base, diffused toward the collector junction depletion region. Okay, all right, and let's move on to the number 3. Let me erase all the notes. Number 3, what is this? This guy and that guy. Number 3 is very simple. That is very conventional and normal, reverse bias current of what? Collector junction, right? So in this collector junction has its own reverse biased current. Okay, so this number 3 current can become and build up the base current as well as collector current. So take a look at the color here. Number 2 and part of the number 3 would become the collector current because it is flowing into the collector region, and number 2 is also flowing into the collector region. So this part, number 2, is the main one in determining the I sub C collector current. However, don't forget this is a very tiny amount of saturation current as well, because this NP in active mode, right? This MP region base to collector is reverse biased, so very tiny amount of saturation current can contribute to the collector current. But however, this amount of saturation current is too small to take into account collector current, so just ignore it. And this number 2 is the main one in building up and in composing the collector current. Okay, but and this part, the black colored one, is now flowing into the base part. So this current flow, reverse biased saturation current from collector to base, would contribute to the base current as well. So that is the main reason I have write down the base current here. Okay, and now take a look at the number 4. Number 4 is, part of the holes are now injected into the base region, and part of it has been used to recombine with electrons in n-type region. So this number 4 indicates recombination current. So electrons in n-type base recombine with what? Yeah, with the holes in the quasi-neutral base region. I mean, once hole has been well injected into the quasi-neutral region of base, always think about the depletion layer here and there, emitter junction and collector junction, right? So once hole has been well delivered to the quasi-neutral region of base, and part of holes can be used to recombine with electrons in n-type region, okay? So this recombination current can become another part of the base current. So this number 4 would make base current. Okay, and the last one is number 5. So number 5, that means, think about that this emitter and base junction. This PN junction is forward biased. That means electrons in this N side, right, can be injected into the P side as well. However, how come this whole, the thickness of this arrow, very thick, but this thickness is very small, very thin. Why is that? Yeah, one-sided PN junction. Can you see that? P plus N. So many holes can be injected into the base, but less amount of electrons can be injected into the emitter. So the main current flow can be flown from emitter to base and current, instead of the main current component from base to emitter. So that is the main reason why the emitter should be very heavily doped and base should be relatively lightly doped compare against the doping concentration in emitter. So later on, the emitter concentration, base concentration, so emitter doping concentration should be much, much higher than the base doping concentration. So in PN junction diet, PMP BJT, people are saying that PMP, but from the perspective of device engineer, that should be P plus N P BJT. Otherwise, the simple PMP transistor may not work perfectly as an ideal transistor. Okay, let me see. Number 5. So number 5 is electrons. Definitely, electrons are injected into the quasi-neutral emitter region, right? So beyond the depletion layer, the electrons in the N side can be injected into the P side because this emitter to base is forward biased. Okay, all right. So number 5 can give us the collector emitter current, part of the emitter current. Okay, so this would affect the emitter current. Okay, I guess that's all for this lecture note. And before moving forward, before moving to take a next movie clip, please have your own time. What would be the device design guideline in PMP-BJT? Well, the answer can be found in the next lecture, next page. But before reviewing it, please have your own time. What kind of current component can be found and occurred across this PNP BJT, and think about now emitter junction is reverse forward biased, collector junction is reverse biased. In this active mode, how the electrons and holes here and from region A to B, how they are moving, and what is the main physical origin for each current component, IE, IC, IB. Think about that and more. Okay, then you may have your own BJT device design guideline. Then that would be perfect. Okay, please have your own time and see you in the next movie clip. Bye bye.